weak acids and weak bases. And we did calculations for the weak acids and weak bases last time. Okay. And the way that we're going to do it is we just use equilibria to determine the pH of the weak acid and weak base because they don't undergo 100% dissociation. Okay. So if we have what we call problems that deals with weak acid and weak bases, most likely the Ka and the Kb are given for the one that is being asked. Okay, we might not have enough example that we have in our lecture, but I would suggest you go over, okay, the reviewers that are posted there because most of the questions there, okay, deals with calculation, even the full problems for chapters. And the way I put the solutions there is how you're going to solve it using the way we solve problems during class. So we did weak acid, we did weak bases, we even did the pH of salts. Okay. And with the salts, we even try to determine what's the pH of the salt if you're given, let's say, the solution or the concentration of the salt. So whenever we have NaBr, we said that it's going to be a neutral salt. Why? Because this comes from a strong base and this comes from a strong acids, and none of them will hydrolyze with water to give you acidic or basic solution. Unlike if you have ammonium chloride, what will happen? This comes from strong acid. This comes from a strong base, weak base. So the ammonium ion that you have there will undergo hydrolysis. It will react with water, giving you NH3 and H3O plus, giving us evidence that the presence of the H3O plus will make this salt acidic. Or if you wanted to do the way I asked you, since this one came from a strong acid and this one came from a weak base, so the resulting salt will be acidic. So you're going to be asked question, which of the following will be salt, of the following salt will be acidic, basic, or neutral? So those are the type of questions that you're going to do. Now, since we're dealing here with equilibrium, okay, we go to the so-called common ion effect. So common ion effect is the presence of an ion that is common to a given solution. So if you remember in your chapter 14, so we say when you have a reactant and you have a product, and what happened there, when we say there's a common ion effect there, you're adding one of the what we call sides. So maybe you can add the concentration of the product. So what is the common ion effect on that? So if you add the more product here, what will happen to the shift in the equilibrium? Which one is favored? Anyone? If I have this system, A plus B producing C plus D, and I add more D, what happened to the system? Hello? What happened to the system when I add more of the product? So usually it will shift the equilibrium going to the backward. Okay? It shifts the equilibrium to the left. So if you add, okay, more C here, so what will happen is it will shift the equilibrium also to the left, or it favors the backward reaction. So what is the common ion effect here means? So let's say you have what? HA And then it dissociates to give you H plus and A minus. But the problem is you also have the presence of A minus from another source. So that is the common ion effect. So there is an ion that is common, okay, to a acid or base that you added to the solution. So when you have a common ion effect, just like what happened when you add more products to a system at equilibrium, it's going to shift in an ionic equilibrium caused by the addition of a solute that takes part in the equilibrium. So this is still just a continuation of your concept of equilibrium. So how does this common ion effect seen? So the best example of the common ion effect is what we call the buffer. So when you have a buffer system, this is a buffer, what we call it's a solution that's characterized by the ability to resist changes in pH when limited amounts of acids or base are added. Okay. So usually when you have a buffer, it resists drastic pH change. And a buffer is made up by combining weak acid and its conjugate base, or a weak base and its conjugate acid. So if we're going to look at this, buffer is just an application of a common ion. Okay, the presence of a common ion usually suppresses the ionization of a weak acid or weak base. Okay, so what's the buffer system that you know? In our body, what do you call the buffer system? Why is it our stomach, which is made up of gastric juices? So what is the acid associated with gastric juices? Anyone?
Isn't it hydrochloric acid?
Okay, so you have what we call HCl. Okay, now why is it HCl in your stomach? It won't burn your stomach. I don't know if you've seen some movies when some characters, they're contemplating suicide and they drink something like pesticide or other thing. What happened? What happened to their mouth? So maybe if you've seen a movie of a student who failed chemistry exam, oh, I'm not going to pass the course. So what happened? Whenever you see a movie where people try to drink something, you see their mouth what? Foaming, right? What's the explanation that you can get there? Why is it your mouth when you ingest something that is not palatable to your stomach, you see the foaming of the mouth? The main reason there is the body try to remove whatever you ingested, and in doing so, it pushes back that material out of your mouth, and in doing so, you release what we call some HCl. Or sometimes if you just vomit too much, some of the HCl get out of your mouth, and it tastes so what? So sour. Okay? So why is it foaming? Because the HCl is burning the skin in your mouth. Now the question is, why is it that when it is in the stomach is not burned? What makes it maintain the pH around 7.4? Anyone? The answer there is in your slide. The presence of what we call the buffer system. Now the question is, what is our buffer system? Anyone? What's the buffer system that keeps our pH under control? That's why even if you drink this so-called alkaline water, your pH body will not change.
Our blood.
So what is the buffer that the buffer system that we have that keeps the pH in our body at around 7.4. Anyone?
Isn't your stomach lined with like mucus that doesn't burn the inside of your stomach?
No. What's the buffer system? I think the bio should, has discussed some of this. I'm not sure. It's not blood. So what is the fuel of our body? Okay.
Carbonic acid.
So the buffer system that we have is just known as the phosphate.
Oh, I knew that.
What's our fuel in the body? We have what? ATP, right? So what does the P stands for there? Phosphate. So ATP going to what? ADP or vice versa. So what will happen there is, okay, you have a lot of phosphate in your body, and the phosphate buffer, that's the one that maintains the blood that we have. And as you can see, phosphate is a weak acid. So whenever you have what we call the buffer system, it's made up of a weak acid and its conjugate salt. Okay? So if you have a buffer system, usually it's a weak acid and it's conjugate salt. Or its base and its conjugate salt. So for instance, if we have acetic acid, so that means its conjugate base is CH3COOH. So how does it act with the acid that is added to the system? So when you add an H3O plus, one of them will react. So in this case, the base form, giving you CH3COOH plus H2O. When a hydroxide is added, okay, the weak acid will be the one to react with it, giving you CH3COOH, no, COO minus plus H2O. So there is no H3O plus or hydroxide that remains unreacted. So the system will act on it. The buffer system will act on it. Okay? And if you have an ammonium system, NH4 plus and NH3, so when you add an acid to it, the basic form will react on it, producing NH4 plus and H2O. If you add a hydroxide on it, the acidic form will react to it and you form NH3 and H2O. So as you could see, those two forms are always there. So that's how the mechanism of a buffer. So let's try to get, how do we determine the pH of a buffer system? Like for instance, is made by mixing 1 liter of 0.020 molar benzoic acid with 3 liters of 0.06 molar of sodium benzoate, given the Ka for the benzoic acid as 6.3 times 10 to the negative 5. So how are we going to solve this? So the first thing that we can do here is maybe look at the new concentration of your benzoic acid, because what will happen? You have 0.02 and then you use 1 liter of that, mix it with 3 liters. So I divide it with the new total concentration. So this is what? 1 plus 3, so I have there 4 liters. So the same thing with the benzoate. I have there 0.06 molar. I have 3 liters of that mixed with 1 liters of what we call benzoic acid, so over 4. So that's the new concentration that you're going to use in the ice table. So how do the ice table or the rice table would look like? So I could put it like this, HBC. reacting with water, producing H3O plus and Bc minus. So I will have here in the initial, I have what? What's the number that I will get here? 0.02 times 1 over 4. Anyone?
0.005.
So that will be 0.05. Or 0.005. I think I missed. And what do I have in the water here? None. How about this one? I'm going to add whatever the number that I have there. So that's just 3/4 of 0.06. So that's 0.045. Now, do you see the difference now of a common ion? So the common ion, you already see there that initially, it's not only the starting material. You already have one of the product starting concentration because you get it from another source. So what's the changes that we have? So this is minus x, this is plus x, this is plus x. This is close. And with that siren, I celebrated my 1 year of teaching online. It's been a year since we moved to online teaching. So if you're going to do it, this is 0.005 minus x, and this is x, and this is 0.045 plus x. So how are we going to solve the problem? So you're given the Ka there. So that is equals to x times 0.045 plus x divided by 0.005 minus x. Now, we can always have an assumption here that 0.045 plus x is just 0.045 and 0.005 minus x is just 0.005. It's okay. And with that, what will happen? You will have 6.3 times 10 to the negative 5 equals to 0.045 times x over 0.005. So solve for x. So I cross multiply it with that one and then divide it with 0.045. So do it yourself. What's the x? So if I'm going to do the operation on that, it will be 6.3 times 10 to the negative 5 times 0.005 divided by 0.045. So what that would be? So I get, anyone? 7.0 times 10 to the negative 6. Are we done? The answer is not yet done because we are asked for the pH. But what is X? X is your H3O plus. So all you need to do to get the pH, you just get the negative log of H3O plus. You get 5.15. Question. Now, this is the long way. There is a shortcut in solving this problem. Okay? And we have another problem that we have here, but I'm not going to use this to solve the long way. I'm going to use now the shortcut in solving problem that we have what we call buffer system. Okay? So this is using the Henderson-Hasselbalch equation. So buffers of specific pH can be prepared using the Henderson-Hasselbalch equation. So the way that you look at this Henderson-Hasselbalch, it is the notion that buffers are prepared from a conjugate acid-base pair in which the ionization is approximately equal to the desired H3O plus concentration. Because whenever we prepare buffer, we look at it in terms of the pH. At what pH are we going to apply the buffer? Okay, so what is this Henderson-Hasselbalch equation? So if you're going to derivatize or to derive the Henderson-Hasselbalch equation, you can start it with this notion of what? This is your Ka, right? Because you have the presence of your hydronium ion. And if you're going to look at the hydronium ion, you have what? Ka equals to H3O plus times A minus over HA. Now, what if instead of that arrangement, we solve it in terms of A, in terms of what we call the hydronium ion concentration? And what do we do? Okay, so we solve it in this arrangement, or rearrange it in this arrangement, and then we get the negative log. So if we get the negative log of all sides, so this is what we have, log, negative log H3O plus, negative log times Ka times HA divided by A minus. And then we distribute it, we get a negative log of Ka and then the negative log of HA and A over A minus. Now, what is negative log H3O plus? Isn't this equals to what? Negative log of H3O plus is equals to your
pH.
pH. And negative log of Ka is equals to your pKa. And to make this positive, okay, what do you do to make this positive? You swap the numerator and the denominator. So what you end up getting is the Henderson-Hasselbalch equation. Now let's try to use it in our previous problem. This one. So I'm going to, I want you to remember the 5.15. I'm just going to clean it up. Oh, I didn't clean it up. So I'm going to go back again. So let's say instead of doing that long calculation, we use the Henderson-Hasselbalch equation. So how are we going to solve this? So we have the pH equals to pKa plus log of, if I'm not mistaken, that's log of base over log of acid. Because you have there an A minus and an HA. So what we're going to do here, so I need to get the pKa of this. So this will become negative log 6.3 times 10 to the negative 5. And then log, so which is my acid and which is my base here? Do I need to use this one and this one, or I need to use the new concentration that they have when they were mixed? Anyone? Because I think this now become what? 0.005 molar, and this become 0.045 molar. So which one I'm going to use? Will I use the 0.06 and 0.02 or the 0.005 and the 0.045? Okay, since they're already in a mixture, I'm going to use the new resulting concentration. So I put here 0.045 and I put here 0.005. Now what do you get? Negative log 6.3 exponent negative 5. So that will give me 420. 0.045 divided by 0.005. So that will give me 9. So what is log of 9? So I have here 420 plus 0.95. And what do I get? 5.15. Is it the same as the one that we solved earlier? Are we still going? Are you still going back to that long way when you know you can have a shortcut? Or you just wanted to do it this way, as the other calculation would ask here? So how do we solve this one? So again, we use pH equals to pKa plus log of the base over the acid. So whenever the Ka is given, all you need to do is get the negative log of that 6.8 times 10 to the negative 4 plus log. So this is the what we call crucial part. You have to identify which is the acid and which is the base. So the base is in the numerator, the acid is in the denominator. So how are you going to solve this? Anyone? What will I put above and what will I put below the line?
Is sodium fluoride the base?
So I'm going to put 0.2 where?
In the numerator?
Anyone who beg to disagree? So NaF is not the acid, it's not the base. What is the base? That's the base. That's the conjugate base of HF. Okay? So if you have that problem, you put at the setup negative log of 6.8 exponent negative 4. So this is what? 3.17 plus log of 2. So this will give you around 0.30. So you will have what? 3.47. Can you assure me you can get a correct answer here? What's the common mistake that you will going to do here? You don't know which is the numerator and which is the denominator. How are you going to be sure? The numerator will have one less hydrogen than the denominator. Question? Before we go, one more buffer problem, but this is the typical problem that will come up in your exam. Which is fortunately or unfortunately for you is a multiple choice. So my advice is double check your answer. Because if you don't double check, you press an error, or let's say you swap the numerator and the denominator, I can assure you 100% the number that will come out there is one of the choices. So question? So let's go to the next, what we call slide. So just to remind you, the equation is generally shown as pH equals to pKa plus log of base over the acid. So this is the Henderson-Hasselbalch equation. So let's try to use the Henderson-Hasselbalch equation in another problem. So what will be the concentration for a buffer solution that is 0.25 molar in acid and 0.6 molar in the corresponding salt if the weak acid is equals to Ka 5.8 times 10 to the negative 7. So instead for asking for the pH, it asks for the hydronium ion. But if you're going to solve it, it's just the way how you solved the previous problem, where you have the pH equals to pKa plus log of base over the acid. So after you get the pH, you're going to convert this to H3O plus. But the concept or the way that we solved problem before is just the same. Okay, so you have what? Negative log of 5.80 times 10 to the negative 7 plus, so which is which? So it's already said there thing. So you might say, how can this be the base? Because usually your conjugate base will come from a salt. Your conjugate acid will also come from a salt. Okay, so you end up writing this what? 0.60 over 0.250. And what do you get? 5.80 exponent negative 7. So negative log 5.80 exponent negative 7. So I will have here 6.237. I need to use 3 because I have 3 significant figures there. And then log of what? 0.6 divided by 0.250. So that's 2.4. And that would be equals to 0.380. So if you're going to add it with 6.237, you will get this value. But this is not your final answer yet, because your final answer is H3O plus. So 10 raised to the negative 6.617. So you will get around 2 point. What do you get? 2.42 only. Oh, 2.42 times 10 to the negative 7. My bad. It's not pH anymore. Analyze. Question. Question? That's all about the buffer that we're going to discuss. Okay. So how are you going to identify if you have a buffer system? Anyone? It's always made up of a weak acid and its conjugate base, or a weak base and its conjugate salt. So those are the type of questions that will come out in the exam. Which of the following can be a buffer? Which of the following is not a buffer system? Okay. Now, the last topic that we have is what you did in this week experiment, acid-base titration, and next week experiment. Okay. So titration is just what we call a volumetric method. So when we say volumetric method, the root word that we have there is volume. Okay. So in the titration that you did this week, usually it's just the mole of your acid reacting, giving you at equivalence point the same moles of the base. So where do you get the moles? In your experiment for the acid, it's the mass of your KFC over the molar mass. For the base, it's the concentration times the volume. Okay, so whatever way you're going to do, you end up with what we call the moles. Now, in an acid-base titration, what happened? You're either adding an acid or a base, okay, to a base or an acid. It's not always that NaOH is the one that you're going to add. Experiment 18 and 19 will tell you that, but when you go to experiment 22, if I'm not mistaken, you're going to add acid instead of the NaOH. The only thing that is common here is you have your burette and you have your receiving vessel. So either this is the acid and this is the base, or this is the base and this is the acid. So the way that you're trying to do in the acid-base titration is at equivalence point, where you see the snake here and you see this what we call That's the volume at your equivalence point. And in theory, that's where you have the same number of moles of acids and bases if it's a 1:1 mole ratio. In your experiment, the one that is being asked, if I'm not mistaken, in the first part is the molarity of your NaOH, and in the second part, the amount of your KHP in a given unknown mixture. Okay? For those who did already the experiment, you're familiar with this, what we call acid-base titration curve. So usually you have it like this. And for this week, this is how it looks like. So this is pH, this is volume of your what? Volume of what is this? Anyone? This is the volume of what? An acid or a base? Which one? So if you have a titration curve like this one, what are you adding to the system? Is it an acid or a base? Hello? Is this an acid or a base? Anyone? What are you adding? If you have a system that like this, the pH is going up. Because you can also have a system like this one. Okay? So if you have a system like this, you're adding base on it. Why? Because the pH is increasing. If you have a system like this, most likely you're adding an acid to it. So it's not always base that is being added. It depends. Okay? So this is what we call the titration curve. Now, what information does the titration curve gives you? So the titration curve, its most important information that can be conveyed out of it is the equivalence point. And if you're going to look at the different, what we call indicator, this is what you have. So the penophthalate that you use, it changes color when the pH is between 8 to 10. If you're using what we call bromcresol green, the pH should change around 4 to 6 or 4 to 5. So you're just trying to look at the what we call region where they change. Because what happened at equivalence point? What happened? Which is present in excess. So if you have here the mole of the acid, that is also equals to the moles of your base. So if you have a strong acid reacting with the strong base, your equivalence point is exactly at pH 7. Now, what do you think happened when the titration is between what? A weak acid and a strong base. Where do you think is the equivalence point? What's the pH of the equivalence point? Okay, if I put here A, B, and C. So these are the choices. So what is the pH of the equivalence point when you're titrating weak acid and strong base? Anyone? Because those are the type of question that will come out. Or what will happen if you're going to titrate, let's say, a strong acid versus a weak base? So what will be the equivalence point? So if it's strong acid versus strong base, it's equals to 7. But what happened if it's between a weak acid and a strong base? Where is the equivalence point? Anyone? you don't answer this, I will leave this question and I leave you up to look for yourself if that questions come out in the exam. So what do you think is the equivalence point when it is a titration between weak acid versus a strong base? Why C? Which is stronger? Let's say you're titrating acetic acid versus what we call NaOH, or maybe the one that you have this week. Anyone? Anyone who did the experiment this week? You have a KHP, which is a weak acid reacting with NaOH. So what is the equivalence point? Will it be 7, above 7, or below 7? Okay, so if you're going to look at your data, usually it's above 7 because you have a basic there that is much stronger than the weak acid that you have. And definitely when you have a strong acid versus a weak base, okay, the equivalence point that you have, so this one will just become what? Less than 7. So maybe this will be around, if I'm going to change this one, I have here 6, I have here 4. But if I have what we call a strong base reacting with weak acid, I have here, let's say, a 7, and I have here a 9, and that's the equivalence point that you have. Okay? So if we have what we call the region of what we have here, because there's only what we call 3 region here. Before equivalence point, after equivalence point, and at equivalence point. So it's easy if you have both strong acid and strong base, because it will always be at 7. It's a little bit complicated if you have a weak acid with strong base or weak base with strong acid, especially with regards to the calculation that we're going to do on that. So the equivalence point, as I told you, that's the point of titration when you have a stoichiometric amount of reactant has been added. And at this point, your indicator should change color near the pH of the equivalence point. Okay? And when you solve, when solving problems in an acid that reacts with the base, the first thing that you need to know, who is the one controlling the reaction? When I say who is the one controlling the reaction, which is the limiting reagent? So you have to recall the concept that you learned in your Gen Chem 1. So usually the limiting reactant is the one present in what? Less or more amount? Just like your what we call chemical equilibrium. Which is the limiting reactant in part A? Is it the Fe3 plus or the SCN minus? So the same thing here. You have to know which one is present in less amount, because that's the one that will control the reaction. And then the next step that you're going to do is to review what remains at the end of the reaction. And the one that is present in excess, that's the one that dictates the pH of the solution. Okay. Now, if both of them were utilized, so we could say the solution will become normal, especially if it's a weak acid, strong acid and a strong base titration. But if you have a weak acid and weak base, okay, you form a salt, and then after finding the salt concentration, you're going to use the hydrolysis equilibrium to find the pH. So you're going to apply here now all knowledge that you have about the pH. So I have 2 problems here. One, strong acid, strong base, and the other one, weak acid, strong base. Okay, so let's go with this one. Calculate the pOH and the pH of a solution in which 10 ml of 0.1 molar HCl is added to 25 ml of 0.1 molar NaOH. So what do we do here? Okay. We can do here, what we call calculate the moles of your HCl and the NaOH, and then determine which one is in excess. Okay. So if you're going to look at the reaction that you will have here, this is what? HCl reacting with NaOH, producing, what do you produce? Water and a salt. So the way that we're going to do is let's account the moles of the HCl. Let's account the moles of the NaOH. So how do we account the moles of the HCl? Can we just do it like 0.1 moles per liter over or times 10 ml divided by 1,000 ml per liter? The same thing what we do here. So you have 0.1 moles per liter times, I hit this pad of mine, 25 ml over 1,000 ml per liter. So what's the number of moles that I get? Anyone? So you get here around 1.00 times 10 to the negative 3 moles. And you get here around 2.5 times 10 to the negative 3 moles. So which one is limiting? Okay, so the limiting is this one. So what does this mean? At the end, all of this will use up. And the same amount of this will be used for NaOH, leaving you with what? (1.3 times 10 to the negative 3 moles of your hydroxide. Now, what's the next thing that you're going to do? You're going to divide this with what? You have
The volumes added together.
this one. So you divide it with 40 ml divided by 1,000 ml per liter. And you're going to get here a new concentration that is in molarity. And what do you have there? Is that the POH or the pH? So 1.5 times 10 to the negative 3 divided by 40 divided by 1,000. Oh, is it 40? No, it's 35. My bad. Why is it 35? Because I have a 10 and a 25. So what do you get? 4.29
2.9
times 10 to the
-2.
So this is what? OH minus or H3O plus?
OH minus.
So that's why you're going to get the POH. And that would be equals to what? Negative log of 4.2 times 10 to the negative 2. So what do you get? POH equals to
1.36.
so 1.3,
68.
okay, 68. And to get the pH is just equals to 14 minus 1.368, giving you a pH that is equals to 12.632. Analyze. This is the easy one. Because if you have strong acid, strong base, whatever the concentration, that will remain the same because they will undergo 100% dissociation. Because the next one that we're going to do is, what if instead of a strong acid and a strong base, we have a weak base and a strong acid? Like this one, you're asked to calculate the hydroxide and the pH at the equivalence point for the titration of 500 ml propionic acid, 0.1 molar propionic acid with 0.05 molar calcium hydroxide. And the Ka of the acid is given as 1.3 times 10 to the negative 5. So how are we going to analyze the reaction? So maybe we can determine the moles of the acid. I'll just put it as HA because it's a weak acid. So that would be equals to what? 0.1 or 0.1 times 500 over 1,000. Giving you what?
0.05.
5 times 0.1. So you have 0.05. So that's the amount of your acid. And if you're going to look at the reaction here, so you have calcium hydroxide. So that's 2 of hydroxide for every reaction. So that means you need 2 of the acid to give you how are we going to do this? We have 2H2O and CaA2. So the question that we're going to know now is, we know this as what? 0.05 moles. So how many, oh, not that one, it's this one. So how many moles of calcium hydroxide do we have? Anyone? So if we have 0.050 moles of the propionic acid, how many moles of calcium hydroxide do we have at equivalence point? Can we say 1/2 of that? Everybody see why is it 1/2, or you want to ask the question, why? So to those who wonder why, so what we're going to do is we get the moles of the calcium hydroxide. So for every 0.05 moles of your HA, so you have there what? You multiply it 1/2. Where did we get the 1/2? 1 mole of calcium hydroxide per 2 moles of HA. So that's why we end up with 0.025. You still have the question, why? Everybody got where I got this number? Now, what else do we need to do with the calcium hydroxide? So we're given the number of moles. We also need to determine the volume. Okay. Can we determine the volume? Now we have the number of moles and the concentration. So all you need to do is what? 0.025 moles divided by 0.05 moles per liter. Molarity is defined as moles per liter. So how many liters do we have here? What's the volume that we have here?
0.5.
Okay, so you have what? 0.5. Now, why do you think I need to get this volume? Why do you think I need to get this volume? Because what will happen to your HA? It's thus dissociate to give you H plus and A minus. And which one of them will hydrolyze? Anyone? Which one of these two will hydrolyze? A minus. So if that hydrolyze, I will have a reaction A minus plus H2O giving me HA plus OH minus. Do you follow? I need to get the exact concentrations of this. All I know as of now, I have a 0.05 moles here that also produce a 0.05 moles here. Why? Because I reacted with hydroxide, and the hydroxide will force it to dissociate 100%. Now, what is I'm missing now so that I can get the concentration of my A minus? I need the total volume. That's why I need to get the volume of the corresponding calcium hydroxide that reacted with propionic acid. So since this is just 1 liter, so I could say I have here 0.05. Analyze. Because this is now your rice table. So you don't have anything here, you don't have anything there. That's the initial. And then the changes that you have. And then the equilibrium, so 0.050 minus X, and then you have X here and X. So what do I have here, Ka or Kb? I think that's the first question that you have there in your chapter reviewer. So what do I have here? If I'm going to what we call put the thing here, will I have a Ka or a Kb? Okay, so you're going to have there the Kb. Why? Because I have here a hydroxide in one of the product. If I have hydronium, that's Ka. So can I get the Kb? Yes or no? Because the one that I've given here is Ka. Can I get the Kb from the Ka? The answer is yes. Okay, so you have there 1 times 10 to the negative 14 divided by 1.3 times 10 to the negative 5. And then you're going to put all those matters that you have here. So I need to put another what we call worksheet here or whiteboard. So I have here Kb equals to the hydroxide that you have there times your HA over your A minus. And then I'm going to get there as what we call 1 times 10 to the negative 14 divided by the given Ka, which is 1.3 times 10 to the negative, is that 6 or 5? I want to do 5. And then I have here what? X times X over 0.05 minus X. So what is my new Kb there? Anyone? So this now becomes 7.7 times 10 to the negative 10
10.
equals to x squared. And as usual, 0.05 minus x is just equals to 0.05. And you can also make the assumption that the initial concentration divided by the given Kb, okay, is over the 1,000. So you end up with what? What is x here? So it's just the square root of 7.7 times 10 to the negative 10 times 0.05. And that is equals to what?
6.20 times 10 to the power
So
negative
x is 3.85 times 10 to the negative 11. And that is your hydroxide. So you get the POH. Oh, wait, I think I made a mistake here. So the x is equals to 3.8 times 10 to the negative 11. That's the x squared. So I still get to get the x of that. So what's the x again?
6.20 times 10
6.20.
to the power negative 6.
And then you get the POH. I get 5.21. So to get the pH, that's 14 minus 5.21. I get around 8.79. Analyze. Question? So the coverage of our exam is until this point. Sorry for the background music. So question. Ooh, 66. Nice weather. The quizzes are what we call, when we compile everything, it's one exam that will replace the lowest exam. That's how the quizzes are. Most likely 25 questions, 25 times 4. I don't know, maybe we will change it, but you will know about it. Yep. So if the average of all your quizzes is higher than the lowest exam, then it can replace your lowest exam. So question. So we still have time. We will proceed with chapter 17 next meeting, and then maybe the last 40 minutes we will do for open question if you have any question. But you know how the exam will be. You just need to go over all the reviews that you have. Question? Pregunta? So more or less, you only have what? 5 more weeks. So after this week, you have 19, 20, 21, 22, 23, 5 more experiments. So in that, what we call remaining weeks that you will have how many exams? At the most 3. The second, the third, and the final exam. So what's the question? I still have 10 minutes to go over any questions that you have. So most likely you have 25 items because times 4, that will give you 100.
Are you going to send us the reference sheet or post the reference sheet with the equations that we're going to get on the?
Well, the usual thing, maybe you will have it on Monday or Tuesday.
Okay, thank you.
We have not done the exam yet. Maybe, I don't know. Or a Monday, whoever's going to what we call attend the lab, can you email me and your maybe phone number? Because if everything doesn't go well or what happened to me on the weekend, we may not do the in-person lab. But you will only get an email if that happens. If you don't get an email, it means all systems go. Because I will have my vaccine shot this Saturday, so I don't know what will happen.
So you want us to email you our phone number?
whoever is going to attend the Monday.
Okay.
Okay, so maybe by 6 o'clock, if I can stand up and walk, then everything's go. But if I cannot stand up, so you're going to get a message as early as that we're going to cancel the in-person class. And the whole class will receive an email when you take the quiz that we might go virtual. But if you don't get anything, that means all systems are okay. So that's to those who are assigned to do the in-person, okay? Because I think if I emailed by 8 o'clock, some of you are already on the way to PACE. So at least by 6 o'clock, if I got your number, you will text again that we're going to virtual. If you don't get anything, so that means everything's okay. So question. The experiment that you're going to do next week is just the same as this week. You're going to have the same setup. I think instead of using a solid, you're going to use a liquid. You're going to use a soda and phosphoric acid. So question, because if not, I'm going to end the class. So everybody's ready for the exam? That's why you don't have any question? Yes. You can type it to me, Monica. Just ask, not everyone. If it's a personal one. Any more questions?
Oh, I have a question. Have you added the chapter 16 lecture recordings to the YouTube
I
link
don't
yet?
think the one that we have this week is not yet added.
Okay.
Also for the owl, for the chapter 16, it shows on the owl assignment that there's 32 parts, but like when I go to the grading, it says that there's 53 parts. Do you know how many there are? Just so like I know for myself.
I don't know. I mean,
Okay.
the OWL system, I just set the date there. Other than that, I don't usually touch anything on it. Any more? Just give the extra credit just maybe 5 o'clock.
For the extra credit, it's only one page, right?
Yep.
Thank you.
So make sure you watch, okay? If you write anything and then you didn't watch, you're going to what we call warn. Okay, I have the attendance even if I didn't attend it.
No, I went.
No, to those who are going to submit, okay? Any more?
You want it double spaced, right?
No, I mean just one page. I'm just answering some of the question here. And to those in my lab, I want you to look at the grades that you get and see where your mistakes so you don't do the same mistakes in the next lab. With regards to the lab grades, they should be returned to you because I myself I'm behind, but I think before the end of the March, I'll be what we call in time with all the lab grades because if I'm not mistaken, I already graded 15. So if I have the time, 16 and 17 should be graded back. Because how you know how you're standing in the lab if they're not going to be what we call graded? It's so hard for me to grade the lab because I have to what we call read the thing. But for Monday group, I already see what we call some sort of they almost